speaker, Borzoo Bonakdarpour, is an associate professor of computer science at Michigan State University. And Borzoo's done a lot of work in distributed systems, computer security in general, also hyperphysical systems. And today he's going to be talking to us about controller synthesis for hyperproperties. Thanks. Go ahead.
Okay, thank you very much, Daniel. Thank you for the introduction. Thank you for organizing this workshop. As Bernd said, this was long overdue. Bernd and I talked about organizing a doctoral seminar forever, and we never did it. So yeah, thank you for organizing this event. All right, so much of the things that I'm going to talk about in this talk is joint work with Bernd Fink-Weiner, based on the paper that we published in CSF last year on controller synthesis for hyperproperties. I'll talk about a few other things at the towards the end of my talk as well. So let me motivate the idea first that why we wanted to study controller synthesis for hyperproperties. So let's consider non-repudiation, where you have two parties, A and B, and these two parties, that Joe did a very nice job in setting up the notion of trust. So A and B don't trust each other, and they want to talk to each other through a trusted third party. And this is without any party being able to deny having participated in the exchange. So the way it works is the recipient of the message obtains an NRO, which is a non-repudiation of origin evidence, and then there is the sender of the message obtains a non-repudiation of receipt evidence, so that both sides cannot deny whether there was an exchange. The protocol essentially has to be effective, meaning that it is possible, so that the protocol does something meaningful, meaning that it is possible to successfully transmit the message to the recipient and then the evidence to both parties. But that's not enough. It also has to be fair. And this is not the classic notion of fairness. Here, fairness means that it is impossible for one party to obtain the evidence without the other party also receiving the evidence, right? So if one party receives NRO, the other one has to receive NRR. So what we want to do is we want to be able to synthesize a protocol that satisfies this framework with the specification, including effectiveness and fairness. And what we want to do is we want to synthesize the behavior of the trusted third party, because the other two parties can behave no matter what happens in the protocol, but the trusted third party is the one that needs to be synthesized here. So here's the actions that each participant can have. So actions of A is, if you can see my mouse, it can send a message. It wants to send a message to B, send a message to T, which is a trusted third party, NRO to B and NRO to T, or it could skip. It may choose to do nothing in some step. B is a little bit different, so it wants to send NRR to A, to T, and then it can also skip. And the trusted third party can do NRR, NRO, and send the message or skip. These are all possible actions that, the set of actions that these three parties can take. Now, we can think of this as a complete tree where A starts the protocol, and the actions that it can take during synthesis should not be touched. In other words, we don't want to tell A what this party can do or cannot do. We don't want to restrict its behavior in any way. However, what we want to do is we want to synthesize actions of T given what A has done. So the dotted lines are, in a sense, uncontrollable transitions that we cannot really touch. We cannot restrict the actions of A, but the solid transitions are controllable in the sense that we can restrict or basically remove some of the actions of T in order to satisfy the specification. And then the same thing happens. So B responds and then T. So in a loop, this is going to continue until it terminates. And then the goal is basically to synthesize the behavior of T and ensuring any arbitrary behavior for A and B. So the question that we want to answer is whether this is possible, and then if it is, what is the complexity of this problem? So the specification that we talked about, effectiveness and fairness, if we go a little bit deeper, then we can break it in two parts. So the first part, which is effectiveness, is there should exist a sequence of actions such that the message that is going to be sent and received, and then the non-repudiation of origin and receipt are also received by the associated parties. And then the other thing is, the other component of the specification is that for all other similar executions of A and B, that means if A and B have, matching executions, then it must still hold that the NRR is received if and only if the NRO is received. So that means any other execution should behave similarly as far as the sending and receiving of NRR and NRO are concerned. So this is an example of a hyperproperty. And we talked about hyperproperties all day long, so I'm not going to elaborate too much on that, but essentially a hyperproperty is a sets of executions. So a hyperproperty is essentially a system-wide property, not the property of individual executions. So hyperproperties have a lot of applications: information flow security, meltdown specter, heartbeat. These are just some examples. And the informal problem statement of what I'm going to talk about is as follows. So we have a controllable plant, P. We have a set of uncontrollable transitions. These are the transitions that during synthesis we cannot really add or remove or change. And then we have a hyperproperty phi. We want to give these three things to a controller synthesis problem and algorithm, and then this algorithm synthesizes a plant P prime such that the union of the plant in the presence of the uncontrollable transitions satisfy the hyperproperty phi. Later on, I will make this a more concrete problem statement, but that's sort of the informal problem statement for now. Let me talk a little bit about HyperLTL. So this is a seminal work by Bernd, Marcus Rabe, Cesar Sanchez, Michael Clarkson from 2014 in the post conference. So the syntax of HyperLTL is as follows. You have quantified statements. There exists pi for all pi such that alpha. So pi is a trace variable here, and alpha is another HyperLTL formula. And then you have phi, which is going to be what we usually call it the inner LTL formula. So it basically follows the syntax of the traditional LTL grammar. Each proposition is annotated by a trace variable. The semantics is that, so from a creepy structure or from a set of traces, you can instantiate the instances of pi. So for if there is an existential, then you pick a trace from the set W and assign it to pi. The same thing for the universal quantifier. Then the Boolean operators are that have the usual semantics. For next and until, the semantics is basically like for a set of traces, you evaluate the inner LTL formula by a synchronous progress of all positions across all the traces. Let me give a couple of examples. So this is one of the favorite formulas that we bump into very often. So for any pair of traces, pi and pi prime, it is always the case that the two traces agree on proposition A. And what this means is, for instance, for these two traces satisfy the formula because they both agree on proposition A in all positions, in all pairs of positions. But these two traces don't satisfy the formula because in these two positions, they don't agree on A. Over here, there is A, but there is no A here. And the same thing here. There is A, but there is no A here. And that's why I call this a synchronous semantics, because we evaluate the positions, we evaluate the traces exactly at the same positions. We recently designed an asynchronous semantics for HyperLTL where the traces can make progress with different speeds. So one can stay wherever it is, and then the other one can make progress, and it has to fare in the sense that each trace has to make progress infinitely often. But we are not concerned about that today. Observational determinism is another example. So for instance, this formula says for every pair of executions, if they agree on the secret input, then they always have to agree on the publicly observable output. Or noninference, these are two formulas that were the first speaker talked about this morning. So for instance, noninference is that if I mask all the secret inputs, then that execution matches with the behavior of low inputs and low outputs. Now, with respect to non-repudiation, which I started my talk about, this formula captures the specification of non-repudiation. So this is the existential that basically says the protocol has to do something useful, which is effectiveness. That means eventually a message is sent and then the NRR and NRR received. And then fairness, there is fairness for A and fairness for B, which means that if the sequence of actions are the same for these, for let's say pi prime, then the behavior of NRR and NRO should also be the same. That means it is fair to A, and the same thing for all actions of party B. So non-repudiation is a HyperLTL formula of the form exists for all. So Kripke structure has the classic definition, set of states, set of transitions. Now we have also a set of uncontrollable transitions, which we usually use show by dotted lines. These are the transitions that the Kripke structure has no control over in terms of choosing which way to go. All right, so now the more formal statement of the problem is that we have a plant in terms of a Kripke structure with controllable and uncontrollable transitions, and we have a HyperLTL formula phi. And the controller synthesis algorithm is going to generate a plant P prime such that it satisfies the following constraints. The set of states are the same. The initial state is the same. The set of controllable transitions of P prime is a subset of the set of transitions of the original one. That means during synthesis, we are only allowed to remove some of the controllable transitions. The set of uncontrollable transitions should remain the same. That means we are not allowed to touch any of the uncontrollable transitions because it's basically not controllable by the plant. And then the set of labels should also remain the same. And of course, at the end, P prime should satisfy HyperLTL formula phi. Now, this is the overall statement of the controller synthesis problem. But we are going to look into different fragments of HyperLTL to study the complexity of controller synthesis. And the reason for that is each of these fragments can capture different types of requirements. So for instance, observational determinism is a for all type of formula. Non-inference is for all exists. Non-repudiation is exists for all. Generalized non-interference is for all exists. We have other examples such as data minimization, which is privacy policy, is for all exist. We have done some work on mapping synthesis where there are even more alternation in the formula. So it is of key interest to study the complexity of controller synthesis and by the same token verification and other problems for different fragments. So that is the reason that we want to study the complexity of different fragments of HyperLTL. We also want to analyze the complexity with respect to different shapes of plants or Kripke structures. And the reason for that is in many cases, session-based and terminating protocols have a tree-shaped or an acyclic shape. So for instance, for non-repudiation, the synthesis problem starts with a tree-shape, complete tree-shape structure. All right, so this is the, in a nutshell, this is the summary of our results. So let me tell you what's happening here. So we have all these different fragments here, all possible fragments, in other words, the existential followed by a universal, and then the opposite of that, and then arbitrary number of alternations, and then we have trees, acyclic graphs, and general graphs. So as expected, the controller synthesis problem for trees is easier than acyclic graphs, which is easier than general graphs. And so now I'm going to give you some of the proof sketches and some of the intuition that, why this is the case. So for trees, we are essentially in the class NP. For some cases, that the problem is easier. So for instance, if the leading quantifier is existential, the problem can be solved in logarithmic time. If there's only one alternation and the leading quantifier is universal, the problem can be solved in polynomial time. For acyclic graphs, the problem becomes a little bit more difficult. We go to the polynomial hierarchy based on the number of quantifiers, and then for general graphs, it goes all the way to non-limit case. All right, so this table summarizes all the things that I want to talk about in the next, let's say, 10-15 minutes. But let's go a little bit deeper. So first, let's talk about trees. So for trees, the problem is L-complete if the leading quantifier is existential. Let me just talk about the upper bound. This is the structure of a tree. And the nice thing about trees is the number of paths is always bounded by the number of states. And the trace lengths are also bounded by the number of states. And by the way, this is all in, the complexities are all in terms of the size of the plant, for where we assume that the formula is constant. So it's a system size complexity. So a very simple algorithm can verify can do the control synthesis for trees. All we have to do is we instantiate the existential quantifiers, and then for each path assignment, we go through all the paths that are universally quantified, and this can be done by a simple counter, and then the verification is again can be done in logarithmic time. So that's a logarithmic time algorithm. The correctness can also be checked in logarithmic time. That's based on another paper that we had a couple of years ago, which analyzed the complexity of verification for all fragments of HyperLTL. Now, when the leading quantifier is universal, the problem becomes a little bit more difficult. So let's imagine we have this formula for all pi1 such that there exists pi2 such that psi. And the intuition of this algorithm is something pretty similar to the marking algorithm for checking the satisfiability of Horn formulas. So we start by marking all the leaves of the tree, and then we go through several rounds. So first of all, this can be done in linear number of rounds because the number of paths is in the tree structure is bounded by the number of states. Then in each round, we basically go through all the marked leaves, instantiate pi1 with that. So pi1 is quantified by this universal quantifier. And then all we have to do is to find a pi2 that satisfies psi. So again, that can be done in linear time. Now at the end, if this is successful for some instantiation of pi2, we leave v1. That's the leaf that we marked for the universal quantifier marked. Otherwise, it is we remove the mark, and then at the end we terminate. This is sort of similar to checking the satisfiability problem for horn clauses. Now, it turns out that we can also reduce the horn satisfiability problem to the controller synthesis problem for HyperLTL, where there's only one alternation with a leading universal quantifier. So this is a simple reduction from horn sat. So let's imagine, so just a quick reminder that horn satisfiability, horn clauses are those that there is only one positive literal in each clause and all other literals are negative, or I should say at most one positive literal in each clause. So first we can transform any such formula to one that there are only 3 literals with one positive literal. So that's an example. And then we have the list of variables. In some cases, if there are more than 4 literals, we can introduce a new fresh variable to do that, which is f. So in this example, we end up having 4 plus 3, 7 variables. And then the reduction is, or the mapping is as follows. We start from the initial state. And then for each positive literal, we introduce one state in the plant. So for f, x4, and bottom, we do that. And these are connected by controllable transitions to the initial state. Then for each clause where a variable appears as a positive literal, we add a chain of states, which is the bit encoding of that clause with the variables that appear, the literals that appear in that clause. And I have no idea why I don't see what happened to this negation 1 here and negation 2. But in any case, so the clauses where each variable appears as a positive literal are now connected to the associated clauses. We do the same thing for the other clauses. Now, for instance, x4 here appears as positive literal in 2 clauses, these 2, and that's why there are 2 chains here. And the bit encoding is that, so for instance, f, which is 0, 1, 2, 3, 4, 5, I think positives do not appear here for some reason. So this state is also labeled by positive, and that's for f, which has bit string of 5. So that's why the first state and then the third one are labeled as positive. So then the formula makes sure that bottom is interpreted eventually as false and top is interpreted as true. And then there is consistency between the assignment of values to the propositional variables. So then the proof is that if the horn clause or the horn formula is satisfiable if and only if there is an answer to the controller synthesis problem. The reason that we chose these transitions that connect the positive literals to the clauses as uncontrollable transitions is that we don't want the controller synthesis algorithm to be able to remove this chain here, right? It has to be forced to make that clause true. Let's go to the case where we have only universal or any number of alternations. So in this case, we can solve the problem in NP, meaning that first we guess a solution to the synthesis problem. So the guess is basically a subset of the states or the transitions, controllable transitions, and then we can verify it. And this verification can be done in polynomial time. So the problem is now in NP for the reduction. That's an easier reduction than the previous one. So our reduction is from 3 sat. So let's imagine we have for this particular example, we have 2 clauses with the 4 variables. So for each clause, we add one of those black states. And then for each of the literals, we have these chains where the chain encodes which negative and which positive literals appear in the clause. So for instance, here x1, so this level corresponds to x1, this level to x2, x3, and x4. And then here x1 is in the first literal appears as a -1, x2 also as a -1, and x3 as a positive literal. And then we do the same thing for the second clause. So x1 as positive, x2 as positive, and x4 as negative. And the formula is pretty simple. We just want to make sure that there is consistency between the chains that remain after controller synthesis. So for instance, for this assignment, if we solve the satisfiability problem for the original problem, this is going to be the synthesized plan based on the assignment of the variables, which satisfies this formula. So you could see that in this case, x2 remains in negative, which means x2 is false. And then x1 is true, and x4 is also false. And that satisfies the formula. It also satisfies the HyperLTL formula. So let me just quickly compare these complexities with the complexity of verification. So as I said, this was done in an earlier paper in CSF 2018, again, joint work with Bernd. So the verification problem is L-complete for all fragments of HyperLTL for trees, whereas for controller synthesis, the problem is a bit harder. So it remains L-complete for the fragment that starts with a leading existential. And then for formulas that start with a leading universal with only one alternation, it's P-complete. And then for the rest of the HyperLTL fragment, it's NP-complete. All right, let's now switch to acyclic graphs. Acyclic graphs are also of interest for terminating protocols. So I'm not going to really go through any reductions here, but let me just say that why we go to the polynomial hierarchy. The main reason is that let's start with the leading existential, which is NL complete. And then when we add one universal in general, we can guess the solution and then verify it in the co of the problem, which is in pi pk. Again, that is the result from our 2018 paper. So essentially what happens is that when we compare it to verification, the problem is pretty much in line with verification, except that it goes one step higher in the polynomial hierarchy, which is expected. So you can think of it this way. The controller synthesis problem has inherently one additional existential quantifier for synthesizing the setup transitions, right? So intuitively, that additional existential quantifier bumps the problem up in the polynomial hierarchy. But both problems are p-space complete, verification and controller synthesis for any number of arbitrary number of quantifier alternations. Which one can argue that it's good news that synthesis and verification are more or less aligned with each other. The other good news here is that this also shows that we can do a lot in synthesizing systems with respect to HyperLTL specifications when it especially comes to session-based protocols and also in terminating protocols without going beyond p-space. Of course, the problem for general graphs is a bit more complex. So let me talk about that. So for general graphs, the synthesis problem is actually completely dominated by the verification problem. So if you can solve the verification problem, you can solve the synthesis problem as well. So for general graphs, as you can see, except the first two, except this case where the verification problem is NL complete for also for the fully universal fragment, but it is NP complete for for controller synthesis, and this is because it was already NP complete for trees. But beyond that, the complexity is exactly the same, and that's because the synthesis problem is dominated by the verification problem. All right, so now let me talk a little bit about a tool that we have, which we used to implement a controller synthesis to some extent. It is still not well tuned for controller synthesis, but we did a couple of simple experiments. So our tool is called HyperCube, which is a bounded model checker for HyperLTL. And so this is based on a paper that we published this year in TACAS, and a tool paper which is currently under review, but it is accessible in archive. So as compared to the classic bounded model checking for LTL, which is a reduction to the SAT problem here, we reduce our problem to QBF. So it's a QBF-based bounded model checker for hyperproperties. And the good thing about this tool is it can seamlessly handle quantifier alternations. Of course, it comes with some caveats. Namely, the tool currently doesn't take into account loop conditions, so we lose completeness. The loop condition is something that we are actively working on right now. The structure of the tool is that it receives new SMV inputs with a HyperLTL formula in a homegrown grammar that we have designed. Then we get the data structure of the input model as a BDD by a parser which is called PyNewSMV in Python. We have a parser for the formula. And then we have another tool, again, homegrown tool, which is called GenQBF, which is written in OCaml. That is the part that, it does all the unrolling and generation of the QBF formulas. Then the quantifiers are added to the beginning of the formula. We give this to a QBF solver, which in this case, it's currently QUABS, which is a QBF solver that accepts formulas not necessarily in CNF form, in any form. And then when the solver returns a response, then we have to interpret that based on the semantics of the bounded semantics of HyperLTL. So I think what I want to convey here with respect to the tool is that we have been able to handle a rich class of case studies. So, for instance, we verified symmetry in hardware, which is the bakery algorithm. We could find 2 known bugs in the SNARK algorithm, which is an algorithm for implementing a concurrent double queue, double-ended queue. So we found both bugs in that. Of course, it takes a little bit more time than the other case studies. We also had case studies for information flow security. One of the things that we are going to do is we are going to look into more cases on information flow, including the ones that our first speaker talked about. Now, one of the interesting features of the tool is that it can also be used for synthesis, especially when we are doing bounded synthesis. And I'll talk about that in a little bit. We also can use HyperCube for testing and test case generation. So for instance, we have used it for mutation testing. The model checker gives you test cases that can run over the implementation. The other cool thing that which is related to synthesis that we can do with HyperCube is adversarial multi-agent path planning. So we can, for instance, do generalized versions of reactive synthesis in the sense that, if you have multiple controllable agents and some adversaries, these come usually in the fragment that is for all star exist star, where for all is for all the adversarial agents, and the existentials are for the controllable agents. So for instance, this is a set of experiments that we did for, again, for adversarial reactive synthesis, where We changed the size of the plant from 10 squared to 30 squared, and then the number of agents and the type of agents. So for instance, here we have 3 adversaries and 1 controllable agent. Here we have 1 adversary and 3 controllable agents. These are 2 examples of the paths that we synthesized for this, one directional bunch of intersections. So for instance, this is the behavior of the adversary, and we have 2 controllable robots that start with from the orange spots, and they all want to reach the green spot, while the adversary is trying to block their way. The other one is the opposite of that, where we have 2 adversaries and only 1 controllable agent. And so what our tool does is we specify the constraints of the path planning using a HyperLTL formula. You can also specify the possible behaviors of the adversary, or just let it go loose and do whatever it wants. And then depending on whether the problem is satisfiable or unsatisfiable, if it is satisfiable, then it gives a path for each possible behavior of the adversary. So we also used the hypercube in order to find a solution to non-repudiation that I talked about right at the beginning of my talk. So remember, this was the formula for non-repudiation, which is of the form exists for all. So the way we synthesized the solution was we basically ran iteratively the tool, because in each iteration it finds a witness to this existential, but but that's almost a trivial solution, because that only has 1 execution. But then in the next round, we sort of add negative constraints to the QBF solver to eliminate that solution and get new ones. So we could synthesize the correct solution to non-repudiation in less than a second, where in 6 steps, this is what the agents and the trusted third party do in terms of sending messages, sending NRO, NRR, and so forth. All right, let me conclude. So I talked about controller synthesis, and so the good news was the complexities are almost similar to the complexity of verification. And I also talked about our tool Hypercube that gives us the framework and the infrastructure for designing scalable algorithms for verification and synthesis. There are a lot of other things that we want to do in future. So for instance, there are other types of hyperlogic, such as HyperCTL star, first order, and so on. We want to do controller synthesis beyond finite-state space, and then we definitely want to do syntax-guided synthesis for HyperLTL. Thank you very much for your attention. I'll be happy to answer your questions.
Thanks very much, Borzoo, for the interesting talk. Questions from the audience? I can do one while people are thinking about it. So you gave kind of this whole spectrum here of different cases of the complexity, depending on the type of system and so forth. And you mentioned a number of interesting extensions right at the end. I wonder, in light of the talk that Bernd gave earlier this morning about probabilistic hyperproperties, if you thought about what, if anything, carries over about the algorithms you described to that sort of case.
Yeah, so that's a great question. So controller synthesis is, at least in the way that we are solving it, is a simpler problem than the reactive synthesis problem in the sense of the scheduler synthesis that Bernd was talking about. So now, whether we can use any results here, I would say yes, in the sense that if you have some idea about what are the things in the system that you should keep and you cannot touch, and in the sense that what are the things that you're allowed to change, then that may make the problem a little bit easier. I have not given it a lot of thoughts in terms of how we can use this type of controller synthesis to deal with this enormous complexity of probabilistic model checking for hyperproperties. But that is something that, as Bernd said towards the end of his talk, that we should look into.
Thanks. Any other questions? Okay, well then, thanks again, Borzoo. And that is it for our invited talks. So the next thing on the agenda is our panel.